Okay, so the top of this page is going to be a little strange for you notation-wise. Let me just talk it through. So polynomial division, the actual act of division could be thought of like this. F of x, our function, divided by g of x, that's the divisor, is equal to a quotient, which ends up being on the top of the division, of course. It's equal to a quotient plus, if I was just writing it out, I would write it as a remainder over the divisor. We're probably not going to write things out so that they look like that. It might come up in homework. If it does, and we get stuck on it, I'll come back and I'll point this out in the notes, and then we'll go from there. This one we will talk about, though. Your homework, you'll be asked to do division and then write the answers in this form. Polynomials, not division, but an actual polynomial, can be written like this. F of x equals q of x, the quotient, times g of x, the divisor, plus r of x, which is how we wrote the answer on the last page, okay? Look at that for a second. F of x is equal to the quotient times the divisor plus the remainder. Look what we did here. F of x, the quotient times the divisor, quotient times the divisor, plus the remainder. You can write a polynomial as the quotient times the divisor plus the remainder. Now, why do we care about whether expressions like x minus 2 are actually factors? Why do we care? Let me go back to the first page and point out that if you have something that's a factor, you know that you have a 0 or an x-intercept. That's why we care. So I'm going to write it, because if x minus c is a factor, then x equals c is an x-intercept. And now that we are at x to the third, x to the fourth, x to the fifth, x to the seventh type polynomials, we don't have a quadratic formula or complete the square trick to just solve things for us. We got to go looking for them. So if we can find factors by using division, we find x-intercepts. The factor theorem goes like this. If f is a polynomial function, x minus c is a factor if and only if f of c equals 0, which means I put c in for x and I get 0 for y. I put c in for x, I get 0 for y. That means it's an x-intercept. Now, what's this little set of parentheses for? There's a famous logic phrase, if and only if, and it's frequently abbreviated as IFF. You might have learned it in geometry, you might not have, but it means a biconditional statement. It goes like this. The if-then nature of this definition goes in both directions. That's what it means. If you have a factor, then you have an x-intercept. It's also true backwards. If you have an x-intercept, then you have a factor. This piece of math, this logical piece of math, is true in both directions as far as if-then statements are concerned. Not all if-then statements are like that, okay? But this one is. When you see if and only if, that's what it means. Okay, here we go. An example. I'm going to actually do long division. 8x to the third minus 1 divided by 2x plus 1. Here we go. 2x minus 1. I'm dividing into 8x to the third minus 1. If I get a remainder of 0, the whole purpose of this, if I end up with a remainder of 0, it means I have found a factor. If I found a factor, I found an x-intercept. Here we go. To get 2x, to be 8x to the third, I multiply by 4x squared. I'm going to go over here and I'm going to write 4x squared times my divisor 2x minus 1. I get 8x to the third, which I was supposed to get, and then I get minus 4x squared. I have to write that underneath here. 8x to the third minus 4x squared. Well, when I try and subtract this, I don't have like terms here. It's okay. I turn this to a plus, I turn that to a minus, I turn this to a plus. Those cancel, and these don't combine, so I just end up with 4x squared minus 1. Now, I try to turn 2x into 4x squared, so I go plus 2x. I go over here and I write 2x times the divisor 2x minus 1. I multiply them out and I get 4x squared, which I was supposed to get, minus 2x. And I write that down here, 4x squared minus 2x. Put a parentheses around it and subtract it. How do we subtract polynomials? We add the opposite. So change that and change that sign. Change the sign of every term. Now these cancel and these don't combine. I get 2x minus 1, which is awesome because that's 2x minus 1. So to get that 2x to be that 2x, I just multiply it by 1, so I put a plus 1 up here. I go over here and I multiply 1 times 2x minus 1, and I get 2x minus 1, of course. So I write 2x minus 1 right here, and I put parentheses around it, and I subtract it. it's pretty obvious to me that if I subtract that expression from that expression, I'm going to get 0, and that's my remainder. So, 8x to the third minus 1 can be written as 2x minus 1, the divisor, times 4x squared plus 2x plus 1, the quotient, plus 0 as a remainder. To answer your question, is 2x minus 1 a factor? Hell yeah, it is. Yes. So what did I just learn from the factor theorem? Since 2x minus 1 is a factor, x equals, if you set that equal to 0, what you're going to do is set that equal to 0 and solve it. So 2x equals 1, x equals 1/2. X equals 1/2 is an x-intercept. That's what we just found out by using long division. Whereas when we started and we had 8x to the third, we didn't really have a way to solve that. All right, next page.